Hello everyone, welcome to Energy Conversion 2 class. We will start chapter 4, that is single phase induction motor. So, going to the introduction first, we use the single phase power system more widely than three-phase system for domestic purposes, commercial purposes, and some extent in industrial uses. Because the single phase system is more economical than a three-phase system, and the power requirement in most of the houses, shops, offices are small, which can be easily met by a single phase system. So why we will unnecessarily go for a three-phase connection? In those cases, for that particular operation, we are going for single phase system. The single phase motors are simple in construction, cheap in cost, reliable and easy to repair and maintain. Due to all these advantages, the single phase motor finds its application in vacuum cleaners, fans, washing machines, centrifugal pumps, blowers, washing machines, etc. The single phase AC motors are further classified as single phase induction motors or asynchronous motors. Next one is your single phase synchronous motors, and third one is commutator motors. Like any other electrical motors, synchronous motor also have two main parts, namely rotor and stator. First of all, we will discuss about the stator of a synchronous motor. Now, the stator. Going to the stator part. As its name indicates, stator is a stationary part of induction motor. A single phase AC supply is given to the stator of single phase induction motor. Now coming to the rotor. The rotor is a rotating part of an induction motor. The rotor connects the mechanical load through the shaft. The rotor in the single phase induction motor is of squirrel cage rotor type. Now, going to the construction again, the construction of single phase induction motor is almost similar to the squirrel cage three-phase induction motor. But in case of a single phase induction motor, the stator has two windings instead of one three-phase winding in three-phase induction motor. So, stator of a single phase induction motor. The stator of a single phase induction motor has laminated stamping to reduce the eddy current losses on its periphery. The slots are provided on its stamping to carry out or the stator winding. Stampings are made up of silicon steel to reduce the hysteresis losses. When we apply a single phase AC supply to the stator winding, the magnetic field gets produced and the motor rotates at speed slightly less than the synchronous speed ns. As we know, due to some losses in the machine, this motor will run a bit less than the synchronous speed ns. The construction of the stator of three-phase induction motor, here single phase induction motor, is similar. Okay, so we can say the construction of a three-phase induction motor and a single phase induction motor is very similar. But except one thing, that is, there are two dissimilarities in the winding part of a single phase induction motor. What are those? Firstly, the single phase induction motors are mostly provided with concentric coils. We can easily adjust the number of turns per coil with the help of concentric coils. The MMF distribution is almost sinusoidal. Except for shaded pole motor, the asynchronous motor has two stator windings, namely the main winding and the auxiliary winding. These two windings are placed in space quadrature to each other. Now coming to rotor of single phase induction motor. The construction of the rotor of single phase induction motor is similar to the squirrel cage three phase induction motor. The rotor is cylindrical and has slots all over its periphery. The slots are not made parallel to each other but are a little bit skewed, as the skewing prevents magnetic locking of the stator and rotor teeth and makes the working of induction motor more smooth and quieter. That is, it makes the operation of induction motor less noisy. The squirrel cage rotor consists of aluminum, brass and copper bars. These aluminum or copper bars are called rotor conductors and placed in the slots on the periphery of the rotor. The copper or aluminum rings permanently short the rotor conductors called the end rings. To provide mechanical strength, these rotor conductors are pressed to the end ring and hence form a complete closed circuit resembling a cage and hence got its name as squirrel cage induction motor. As end rings are permanently short the bars, the rotor electrical resistance is very small and it is not possible to add external resistance as the bars get permanently shorted. The absence of slip ring and brushes make the construction of single phase induction motor very simple and robust one. Now, you can note here, we know that for the working of any electrical motor, whether it's AC or DC motor, we require two fluxes, as the interaction of these two fluxes produce the required torque. So now we will go to double field revolving theory. Consider two magnetic fields represented by quantities OA and OB of equal magnitude revolving in opposite directions as shown in figure. Here we can see OA and OB. These are two magnetic fields. Now, this is the point 1, 2, 3, 4. We can see this is the resultant MMF and another magnetic axis is here. Okay, one magnetic flux is here, another magnetic flux is here. We can see two magnetic fluxes and this is the resultant MMF and this is the resultant magnetic flux. So, due to the presence of these two magnetic fields, these two fields will be rotating with their resultant, this vector will be rotating in a direction. So, this is called as double field revolving theory and the waveform for the final AC wave is sinusoidal, that is 1 to 2, 2 to 3, 3 to 4, again 4 to the 1 position. The resultant of the two fields of equal magnitude rotating in opposite directions is alternating, as this is a AC machine. Therefore, an alternating current can be considered as having two components which are of equal in magnitude and rotating in opposite directions. From the above, it is clear that when a single phase alternating current is supplied to the stator of a single phase motor, the field produced will be alternating in nature, which can be divided into two components of equal magnitude, one revolving in clockwise and other in counterclockwise direction. So, if a stationary squirrel cage rotor is kept in such a field, equal forces in opposite direction will act and the rotor will simply vibrate and there will be no rotation. But if the rotor is given a small jerk in any direction, in this condition it will go on revolving and will develop torque in that particular direction. It is clear from the above that a single phase induction motor, when having only one winding, is not self-starting. To make it a self-starting, any one of the following can be adopted, and the methods are split phase starting, repulsion starting, and shaded pole starting. According to the theory, double field revolving theory, a pulsating field of a single phase motor can be resolved into two rotating fields of half its amplitude rotating in opposite direction at synchronous speed. Here we can see these are two different magnetic fluxes having half of its magnitude, direction of rotation of phi Ts, and this is phi Bs, and their magnitude is half of the phi Sm, here also half of the phi Sm, and for this the time t equals to t1 and phi s is 0 here. You can see here phi Ts, phi Bs, these are two different fluxes and this is the resultant of the flux, the phi s. Its value is 0.707 phi Sm. Similarly, here also we can say two different fluxes. Here we can calculate the phi s for time t equal to t3. When time t equal to t4, again this vector will start rotating, and here this is t equal to t5. Again both the fluxes will be rotating but in equal and opposite direction. Now we can see the torque slip characteristic. This side we have taken the slip and in the x-axis we have taken the torque. We can see here this is the first flux phi Ts, this one is the second flux that is phi Bs, this is the resultant flux. Starting from s equal to 0, this is s equal to 1 and this is s equal to 2 condition. Why single phase induction motor is not self-starting? According to double field revolving theory, we can resolve any alternating quantity into two components. Each component has a magnitude equal to the half of the maximum magnitude of the alternating quantity, and both these components rotate in opposite direction to each other. For example, a flux phi can be resolved into two components like phi m by 2 minus phi m by 2, equal but opposite in direction. Each of these components rotates in the opposite direction, that is, if one phi m by 2 is rotating in a clockwise direction, then the other phi m by 2 rotate in anti-clockwise direction. According to double field revolving theory, when we supply a single phase AC supply to the stator winding of single phase induction motor, it produces its flux of magnitude phi m. According to the double field revolving theory, this alternating flux phi m is divided into two components of magnitude phi m by 2.